So here in this video we will do few problems from the past finals that are somewhat relevant to our finals. So this is basically a review, and I'm going over randomly selected problems from the past finals. So the first one is May 2014 problem 1. We're given a matrix A and a vector B, and we have to solve this matrix equation AX is equal to B. And then there is a second question, whether this vector here is also a solution of this equation or not. So for the rest of these problems, what I suggest is that you pause the video right now, try to solve this by yourself, and then continue. Or if you don't know how to start, then see how I'm gonna start this problem, and then pause the video, try to solve it by yourself, and check your answers with me. So basically, what did we say? That the matrix equation, vector equation, and a system of linear equation, they both boil down to what? To create an augmented matrix 1, 2, 3, negative 4. So augmented matrix between A and B, and then we just row reduce that. 3, 6, 9, negative 12, 2, 3, negative 1, 4, 1, 2, negative 1, 1, and then we augment that by the column B, which is 6, 11, 3, negative 2. Now, luckily for us, the pivot is its right place, so let's see. Row 2, I have to eliminate all of these entries here, so row 2 becomes what? Row 2 minus 2 times row 1. Row 1 stays unperturbed. 1, 3, 2, 1, 6. Now I have 2 minus 2, 0. 6 minus 2 times 3 is 6, 0. 3 minus 2 times 2 is 4, so 3 minus 4 is a negative 1. 2 minus 2 is 0, and 11 minus 12 is negative 1. Okay, now the third row, row 3, becomes row 3 minus 3 times row 1, so 3 minus 3 is 0. 9 minus 3 times 3, that's 9 minus 9 is 0. Negative 1 minus 6 is negative 7. Negative 1 minus 3 is negative 4. And 3 minus 3 times 6 is 18. 3 minus 18, negative 15. And finally, the last one, row 4, becomes row 4 plus 4 times row 1. Negative 4 plus 4 is 0. Negative 12 plus 12 is 0. 4 plus 4 times 2 is 8, that's 12. 1 plus 4 is 5. And the negative 2 plus, how much is this? 4 times, so negative 2 plus 4 times 6 is 24, that's positive 22. Okay, so what can I do here? Right away I can, so in order to save some time, right away I'm just going to multiply the second row here by negative 1, and I get this pivot right here. There is no pivot. The second column is not a pivot column, so I have a pivot in the second row and third column, and with that pivot I'm going to try to eliminate these two entries. Okay, so row 3 becomes row 3 plus 7 row 2, and row 4 becomes row 4 minus 12 row 2. And let's see where that is going to lead us. So the first row is unperturbed. Zero, 0, 1, 0, 1, and then 0, 0, negative 7 plus 7 is 0, negative 4 plus 0 is negative 4, negative 15 plus 7 is negative 8. And now 0, 0, 12 minus 12 is 0, 5 minus 0 times 12 is 5, and finally 22 minus 12 is 10. Okay, so here I have row 3 becomes negative 1/4 row 3, and row 5, row 4 becomes 1/5 row 4. So 1 0 0 0, 3 0 0 0, 2 1 0 0, 1 0 1 1, because I multiplied this by negative 1/4 and this one I divided by 5, and then 6 1 2, negative 8 divided by negative 4 is 2, and here I have also 2. Okay, so now I will use this pivot here to eliminate first this one and then the one in the first row. So I have a row 4 becomes row 4 minus row 3, and row 1 becomes row 1 minus row 3. So 1 0 0 0, 3 2, 0 1 0 0 1, 0 0. Okay, so let's see what we have. So first of all, this one, 0 minus 0 0, 0 minus 0 0, 0 minus 0 0, 1 minus 1 0, 2 minus 2 0, and here I have 2. The second row, I did not act on it at all, and the first row is 1 minus 0 0, 1 minus 0 1, 3 minus 0 3, 2 minus 0 2, 1 minus 1 0, and 6 minus 2 is 4. And finally, what do we have to do? I just have to eliminate these two with this pivot right here. So that means row 1 becomes row 1 minus 2 times row 2, and then leads us to 0 1 0 0, 0 minus 0 is 0 0 1 0, and then 4 minus 2 is 2, 1 2 0. Okay, so what do we have? First of all, the vector x, if I will be able to multiply by a 4x4 matrix, has to be 4-dimensional vector, has to have 4 entries, right? So it's x1, x2, x3, and x4. Obviously x2 doesn't have a pivot, so that's going to be a free variable. Otherwise, x4 is equal to 2, x3 is equal to 1, x2 is a free variable, and then x1 is going to be expressed in terms of that free variable. So x1 is equal to 2 minus 3x2, which is t. And from here, the vector x is 2 minus 3t, t, 1, and 2, or that can be expressed as 2 0 1 2 plus t, negative 3 1 0 0. So this is the general solution of this equation. And now the question is whether this vector here is a solution, is a particular solution of this matrix equation. Well, part B, yes, if we let t is equal to 0, then the vector indeed we get 2 0 1 2. So basically we can obtain this vector for some particular t, in our case that t is 0. The next problem asks us to find a determinant of a matrix, okay, and then some question about properties of determinants. Okay, so how are we going to find the determinant of this matrix? We'll use a cofactor expansion. So the determinant of A, or simply, is equal to 2 0 1 0, negative 2 2, negative 1 0, 2 1 0, 6 3 1 1 2. Okay, so it is your choice in deciding what a row or column are you going to choose in order to do this cofactor expansion. So one choice is to take column 1. Okay, So first of all, it's going to be, this is equal to, so the determinant, be careful, this notation means we're looking for the determinant of this matrix. So I have 2 times the determinant of the submatrix created how? When I'm going to delete the row and the column where this entry appears. So I'm left with 2, 1, 1, negative 1, 0, 1, 0, 6, 2. Plus 0 times some determinant, and I don't care what is that because multiplied by 0 is 0. Actually, this is going to be minus because the sign changed, right? So plus minus, now plus 1 times the determinant of what? Of the submatrix created when I'm going to delete the column and the row where that entry appears. So I'm left with negative 2, 2, 3, 2, 1, 1, 0, 6, 2. And finally, plus 0 times the determinant of this submatrix right here, but I don't care about that because I multiplied by 0. Okay, so from a 4x4 matrix, I ended up with finding determinants of two 3x3 matrices. So this is 2 times, and now I do cofactor expansion again. So let's say the third row now. So 0, positive, negative, positive, so 0, minus 6 times the determinant of the submatrix 2, 1, negative 1, 1. So positive, negative, plus 2 times the determinant of the submatrix 2, 1, negative 1, 0. Plus 1 times, and now I can do the same thing. I can choose the same row, so that's positive, negative, so negative 6 times the determinant of the submatrix negative 2, 3, negative 2, 3, 2, 1, plus 2 times the determinant of the submatrix negative 2, 2, 2, 1. Okay, so this is 2 times negative 6, determining 2x2 matrices. Finding the determinants of a 2x2 matrices, we just multiply the entries on the diagonal. So that's 2 times 1, it's 2, minus negative 1 times 1 is negative 1, plus 2 times 0 is 0, minus negative 1, plus negative 6, 2 times negative 1 is negative 2, minus 6, plus 2, 2 times negative 1 is negative 2, minus 2 times 2 is 4. And now simply add these numbers up and you're done. Okay, so this is 2 plus 1 is 3 times 6 is negative 18. This is positive 1 plus 2 is positive 2, plus this is how much? Negative 8 times 6 times negative 6 is positive 48, and this is negative 6 times 2 is negative 12. So 2 times negative 16 plus 6, and then here 36. So this is negative 32 plus 36, and that's equal to 4. So the determinant of this 4x4 matrix is 4. And now the question is, how many solutions does the homogeneous system of this linear equation here have? So it's a homogeneous system, so what do we know? That the homogeneous system can have either the trivial solution, only one solution, unique solution, and it's going to be the trivial solution, the zero vector, or it has infinitely many solutions, right? So one more time, every homogeneous system, which is a times x is equal to 0, that's the definition of a homogeneous system, can either have one unique solution, and that solution is going to be the zero vector, or it's going to have infinitely many solutions. So how these two questions are related? Well, the fact that the determinant of A is different than 0, okay, we know that that means that the matrix A is invertible. And if the matrix A is invertible, then the homogeneous system only has the trivial solution. And that's the vector, the zero vector, the solution. Okay? So it has a unique solution, and that's the trivial solution. Okay, so we're given a matrix here, 1, 1, 1, 1, and it says find a 2 by 2 matrix B such that AB is equal to 0, but BA is not equal to 0. What do we know? We know that the commutative law in multiplying matrices doesn't hold. Okay, so the order of how we multiply the matrices matters. Okay, and we have to find here, we have to find matrix B, so 2 by 2 matrix B, such that A times B will be 0, but B times A will not be 0. Okay, so we have to find the fastest possible way how to do this, because if this is a question on the final, right, you cannot just start trying to figure out a matrix B for which this is going to be 0. So let B be the most, give the most general form of a 2 by 2 matrix B. A, B, C, D. Okay, and then let us calculate how much is AB. So that's 1, 1, 1, 1 times B, A, B, C, D. Now let's multiply this. So the first column dot product of, the first row dot product the first column of the second matrix. So 1 times A is A plus 1 times C is C. Now the first row of A and the second column of B, 1 times B is B plus 1 times D is D. And now second row times first column, 1 times A is A, 1 times C is C, so A plus C, and finally the same thing, A plus D. And we want this, be careful, this 0 here means the 0 matrix. We want this to be 0. But look at this, these two entries are the same, and these two entries are the same. So from here, A plus C has to be 0, and B plus D has to be 0. Okay? Or in other words, take two terms, take any two numbers for A and B, and then the rest of it, C and D are going to be just where A and B is times -1. Okay, so let A be equal to 1, B be equal to 3, okay, and then it implies by this equation, by this here, implies that C has to be equal to -1 and D has to be equal to -3. Okay, so let's check now. A times B, where the entries of B are these, right? So 1, 1, 1, 1 times 1, 3, -1, -3. What do we get? 1 times 1 is 1, minus 1 is 0. 1 times 3 is 3, minus 3 is 0. 1 times 1 is 1, minus 1 is 0. And 1 times 3 is 3, minus 3 is 0. But if you multiply B times A, where this is B, right? 1, 3, -1, -3, times 1, 1, 1, 1. Let's see, what do we have? 1 times 1 is 1, plus 3 times 1 is 3, 1 times 3 is 4. So right away we can stop right here, because this is definitely not going to be the 0 matrix. The 0 matrix, all the entries in the 0 matrix have to be 0. So we'll 1 plus 2. This is also 4, negative 1, negative 4, and negative 1 times negative 4. Okay, so we have found the matrix B that satisfies this. B is equal to 1, 3, negative 1, negative 3. Okay, so here I'm going to the next problem is somewhat similar to the one that we just did. So it says let A be the same matrix as in the previous problem, 1, 1, 1, 1. And let V be the set, so V is some set of 2 by 2 matrices B such that AB is equal to 0. Given that the set V is a vector space, so it's given that V is a vector space, find a basis for V. So how do we do this? Give a general matrix B, A, B, C, D. Okay? And then what is the condition? Let's satisfy this condition. So A times B, in our case 1, 1, 1, 1, times A, B, C, D. And we calculated this. This is A plus C, B plus D, B plus D. This has to be 0. Right? This implied that A plus C has to be 0 and B plus D has to be 0, or simply that A is equal to negative C and B is equal to negative D. Okay? Once we have found the relation between these entries, you go back to the most general vector in this vector space, so A, B, C, D, and now you use this relation between the entries. So I have A, B, now C is negative A, and D is negative B. And now we're going to express this as sum of matrices only depending on A and only depending on B. So this is going to be A, negative A, 0, 0, plus 0, 0, B, negative B. Factor out A, 1, 0, negative 1, 0, plus B, 0, 0, 1, negative 1. These two vectors, they are matrices, but in this vector space, in this context, they are vectors. These two vectors are independent. And obviously, any vector from this vector space V can be expressed as a linear combination of these quote-unquote vectors, right? These two matrices. That means that these two matrices span the vector space V, and moreover, they're independent. So the basis for V is consisted of 1, 0, negative 1, 0, and 0, 0, 1, negative 1. Obviously, I have just two vectors in the basis, so the dimension of V is just equal to 2. Okay, another question involving a vector space. So we're given a vector space V consisted of all the quadratic polynomials such that the polynomial evaluated at 2 is equal to 0. So again, you start with the most general quadratic polynomial, right? So let P of x be equal to ax squared plus bx plus c, right? A quadratic polynomial. And now you have to make sure that this polynomial belongs to this vector space, in other words, that satisfies the given condition. So let's calculate what is p of 2. That's a times 2 squared plus b times 2 plus c, and in order to satisfy the condition, this has to be equal to 0. So that we have 4a plus 2b plus c is equal to 0. And we have some kind of relation here between a, b, and c. So now you have to express one term in terms of the others. And it's your choice which one you're going to take, and based on your choice you'll have different answers for the bases. Okay, there are many correct answers for this question. Let's say that 4a plus 2b is equal to negative c, or simply c is equal to negative 4a minus 2b, right? So in the first step, I just brought c on this side of the equation, it's negative c, and then what is only c? Well, multiply both sides by negative 1, c will be equal to negative 4a minus 2b. Now you have the relation between a, b, and c. You come back here to the most general quadratic polynomial, because that's what our vector space is consisted of, and you say ax or px, which is ax squared plus bx plus c, is equal to ax squared plus bx. And now, as I said, I want to express this polynomial in terms only of a and b, plus negative 4a minus 2b times x. Sorry, there is no x, my bad. Okay, drop the parentheses, ax squared plus bx minus 4a minus 2b. And now you factor out these terms a and b. So if you factor out a, you're left with x squared minus 4, and when you're going to factor out b, you get x minus 2. These two polynomials, x squared minus 4 and x minus 2, are polynomials that span this vector space, and moreover they're independent. Okay, so the basis for v is what? The set of the polynomials x squared minus 4 and x minus 2. Of course, this is only one of the possible, only one of many correct answers. And then the dimension of v, there are only two vectors, only two polynomials in the basis, so the dimension is equal to